Next perhaps 45 minutes or so is to walk you through what has been happening in the area of quantum cascade lasers both in terms of science but more importantly technology and applications. One can speak for long periods of time in terms of the science that has happened in this area, but I'm going to focus more on what it means to a broad range of applications and how quantum cascade lasers have the capability of completely changing the scene, changing the way in which one thinks about these areas. Before I go any further, I do want to thank my colleagues at Pranalika and other colleagues elsewhere who have done enormous amount of work. I'm reporting some of their work, some of our own work. And also I want to thank various Defense Department agencies that have over the years provided significant amount of funding to make all of this possible. That having been said, let me move forward, and this is what I want to do in the next remaining time. First I'm going to talk about where quantum cascade lasers stand in terms of performance. Again, as I mentioned, I will only touch upon some of the scientific advances that have led to the current high level of performance of quantum cascade lasers. Then I will talk about applications of quantum cascade lasers, of two kinds of quantum cascade lasers. One is the Fabry-Perot QCLs. These are broadband devices but produce a lot of power output, and applications have been primarily in the area of defense and homeland security. This includes directional infrared countermeasures, also includes testing of directional infrared countermeasure systems, and then target illuminators and designators and beacons. And then there are of course tunable lasers. Any broadband laser can be made into a single wavelength tunable laser, and those are very useful for detection of chemical warfare agents, toxic industrial chemicals and explosives. And these include both in situ detection as well as standoff detection. Just some preliminaries regarding quantum cascade lasers. I'm sure you are all familiar with quantum cascade lasers, but to complete the picture, they are different. They are semiconductor lasers, but they are different from traditional semiconductor lasers, which consists of a P-type material and an N-type material with a junction. Passing the current through such a device leads to electron-hole recombination in the junction area, giving rise to a photon at the band gap energy of the device. Quantum cascade lasers, on the other hand, are unipolar devices, only electrons so far, and the laser action takes place by transition of electrons between quantized levels of very narrow quantum wells inside the material. Quantum cascade lasers are made out of two semiconducting materials, indium gallium arsenide, indium aluminum arsenide, forming quantum wells as you see here in the active material, and the transition takes place between, for example here, between level 4 and the laser action takes place between level 4 and level 3. So in many ways, it's a much simpler system to think about compared to the junction semiconductor lasers. On the other hand, both the structure design and fabrication are significantly more involved and more complicated. The art of the science of quantum cascade lasers then depends upon how do you provide very efficient excitation or efficient injection of electrons in level 4, which is the upper laser level, and second half is how to remove the electrons from the lower laser level very rapidly so that the population inversion is maintained and high power is obtained. First quantum cascade lasers were demonstrated at Bell Labs by Federico Capasso and his group. First continuous wave QCL was made to operate by Jerome Feist, and subsequent to that was in 2002, and subsequent to that, progress has been very, very rapid. Today, as I will show you, one can make quantum cascade lasers with power outputs in certainly few watts. We are not quite at the level of 10 watts per power level. We expect to get there. But let me move on and tell you what are some of the critical advances that have led to both the high powers, high wall plug efficiencies, and potential for expanding the available wavelengths from quantum cascade lasers to a broad region. One of the things that I forgot to mention is that unlike the case of junction semiconductor lasers such as shown on the left hand side, whose output wavelength is determined by the band gap, in the case of quantum cascade lasers, one can tune the spacing between level 4 and 3 that you see here, thereby changing the output wavelength by changing the thickness of the active layer, thereby changing the thickness of the quantum well. So in many ways, it is possible now to have lasing action over a very broad region by simply changing the thickness of the well. So as I mentioned, that the most important advances have occurred in how one provides efficient excitation to the upper laser level, number 4, and how one very effectively removes the electrons from the lower laser level. One of the things that has happened at Trianalytica is that we have changed the fundamental structure design of the quantum cascade laser very significantly. Traditional way of depopulating the lower laser level is to make sure that the spacing between the levels below the lower laser level 322 and 221 are exactly equal to the longitudinal optical phonon frequency of the material. When you do that, there is a very rapid non-radiative relaxation of the electrons, gives you a rapid way by which you can empty out the lower laser level, which is very good. It works quite well. But however, look at the system. The system now has 3 very significant confining parameters. The separation between level 4 and level 3 is determined by the wavelength that you want from the quantum cascade laser. So for whatever application you have, that part is determined. Separation between 3 and 2 and 2 and 1 is determined by nature. That's the LO phonon frequency of the material. What happens now is that now you have an overly constrained system, doesn't allow any variation, certainly not significant capability of changing other parameters. One of them may be how to make sure that you get efficient excitation in level 4, or for example, you don't have loss of electrons from level 4, which clearly would impact upon the population inversion.